Kole ngambulo luku. With whatever we do. Jioni safu no la. With whatever we do. Hale yide munyu skula. Nyepamne ne kudlukula. Nyepangi ragala gena. Nyepamne ne kudlukula. Ibuloke nongoto ni beti sola. Ibuloke dato ni betoto.
Bigi Congo.
Lamin.
Na?
Lamin te jibe norin te nyamen Lamin.
Kabana wulo kono.
Wulo kono nyinta mo Lamin.
Pabilenki.
Muna ngata afamole.
Haina.
Ngata. Ngoto le. Fabrama.
Mingi. Baba nyole.
Ngoto le Fabrama.
Namu jumala kan kuma diteng.
Fabrama.
Jumala mu.
Ndele bare muso.
Lunda banara.
Famo kata.
Jamani mbere.
Lindo ko.
Jamani.
Bari ngoto man kontande.
Bari jamani fana na ramudu wa kontan.
Ngoto minaka ngalamin je fon filitala. Lamin jibe nori nyala.
Lamin ila siran sama ne benki. Yala so tol sayndi no ko mo lokko momo.
Ngoto.
Nam.
Iterinte yalo ne Lamin hakilo diata bake karambu ngoto. Anu santeng ministry ko di ngole si suoko na amanke ko do holiday
si bitun
bagona de
ala ni ko kede namo balo
ala ni na ko ina karta bulo be damen ala ni je
ngodo
nam
ngoto mon kontan feren
jamani mu ne keda
ifika Lamin ki wulo ko no nyintay mon ko do fete malo Lamin nyande sila la be la moy kala karango
jamani karamol be soron ne ko fasita wulo ko nako
karambu wol ma soron ni ko karambu wol soron da amanke kom holiday lem ngodo dindi ngo nyanta sila la ala karango la moy yamen kamen fue man kontan anda mande
alla nyin kombo kurang adanda la kombo len do la jankara mol soron do kamen kurang ma ra do la kombo e ko ndol fana na karamol soron je karamol soron Lamin ada lo nyino la man tara fe na sokon ala mu nekela
Lamin ite foyde malon kon lesinol be ke kar radio to
nga fine
e ko yana di mod Lamin ya mu na fonye
bi kabin mina kan ntambita nteri maning Fatu ntambite la sukol ala dinngol bebe siri be la moy ka
faru dan so am fana tambira jele ni subala la ngaje dinngol be je talanta nen kili warol e be seri jele
sa Lamin fadante ku kili ko keno la ba Lamin bita ka wulo ko no nyinta mo Lamin
amandara fenela
ite dine ko ni man si yakari lesuno la moy radio to e balon na
mu ne ka ke afonde ba nyara ni alon
telentel jikot
afonde ba mu ne be ke
ite balon tel be jikritel ni man karambe ku kele yaje nata karana mbasa mala ya itarije
par ñarande kombo courant ho findira kombo ide nara yede ni sonka bay ko Lamin manyata la wulo ko aru karam wolbe so da fa ñembe kala
ko to wole nati ba ngalle ni Lamin kuntala kombo courant o ka fa me kombo courant asototal wala kinay ko e sisu kono bari ni ko e sisu kono ibe karangol dike la radio lin telel to hani tele masoto to nyaay man tele soto la bongo bar radio be bulen koto batiri sanga ay si ay alamo
sa do kala nyaadi
ko ta o bulaji
abe o kala nyaadi
kamun ke nyaadi
radio abe wala moy la ibe mona falaje
ibe la karandirol kala jele
ti talle be radio ko men ka karande
ila subject ro baby jele baby jele
wala nanga coco moy fa dan so wolya ngombe tambi kana ngadi ni wolje be ikadum bungo de ko kada maro mo
asototal de
Lamin mala be kara wala de
bari laftalal ideal on ko inde every year second wala fourth
muna ni ko nde ko folle sini lamba nde le sini lo ne ba
mbasa mba foke en koto wole fango yen wulindi yalo famo keta bat yu fana bulata ko ko me yen nati jambi Lamin nyanta karana ntel be jiko be nyineka ya bulay kara wulo kono ta kilar ya bambalo yo be bulaje koto dindi ngoy si ayala le sino la moy radio
wara ka munda kara mo man soro Lamin nyanta kara si so na radio
la sila le ayala le sino
dal ko korno ko smolon
kilar ya
be ngala ko momo sa mi do ni ko no kera
mengi bruzo
ndebe ko do la ba rosa no radio ba no bari woro radio ni abe jele ba do ngamra do man dembe buljan dala nyara nyar wo ko fendi mo la Lamin tayra ba rosa
bara te ku folo ajibe nori nya Lamin tamete ku
teku
bari ko do famo ke
imagine nani nyambol si zol le keje kisiki man si zol no le kafun ka nyoma bari nyambu kilo ni manya na kafindi ni nambe ko zol la ga ni nambe ko zol la ga
ngalle limbeta de be nyambo do dilanna
nyara ni ko rin fennat nyara nata
ko to bari famo ke da
ngata bungono tammi bungono nyara ngando ko fele ko ke baru nganda ni pelo landi jak
iyo awa better la
bungono bismillah bisu diara
ye fongo tanka sina dolu tanka koro ta koro
Hello guys, I am Mr. Yusuf Ajalo and I'm your chemistry instructor. And in our today's lesson, we're going to look at the topic gases. So this is the table of content that we'll go through. First of all, we look at the kinetic molecular theory, properties of gases, measuring pressure, gas laws, ideal gas laws, gas density, partial pressure, Graham's law of diffusion or effusion, and a real versus ideal gases. First, we look at the kinetic molecular theory. And in order to understand the behavior of gases, we work with some key premises. And these premises are gas molecules are in constant motion and therefore possesses kinetic energy. The faster the speed, the higher the kinetic energy. The faster the speed, the higher the kinetic energy. That's the first postulate. And then the second postulate is that the average kinetic energy of a sample of a gas is proportional to the temperature, meaning the higher the temperature, the higher the average kinetic energy. That is the movement of the gas particles. And then the average kinetic energy of a sample of a gas is proportional to the temperature. So that is T is proportional to the kinetic energy. And this means that if temperature increases, the kinetic energy of the gas molecules will increase. If temperature reduces or decreases, the kinetic energy of the gas molecules will also reduce. So we look at the temperature scale. Here we're going to look at 3 temperature scales. That is the Fahrenheit, the Celsius, and then the Kelvin. Okay? And then the boiling point of water on the Kelvin scale is 373 Kelvin. On the Celsius scale, it is 100 degrees Celsius. On the Fahrenheit scale is 212 degrees Fahrenheit. And the water freezes at 273 Kelvin on the Kelvin scale and 0 degrees Celsius on the degree Celsius scale. And then on the Fahrenheit scale, it is 32 degrees Fahrenheit. Temperature, it is important that we can convert between the two scientific units used to measure temperature, that is Kelvin and degree Celsius. Okay? We'll be doing this conversion in our subsequent calculations, that is converting between what? Degree Celsius and then Kelvin. So to convert to Kelvin, we add Celsius plus 273 will give us Kelvin. Okay? Or if you want to convert from Kelvin to degree Celsius, it's going to be Kelvin minus 273 will be equals to degree Celsius. Okay. So a temperature of 16 degrees Celsius will be equal to 287 Kelvin. Let's look at this question. At the equator of Mars, the temperature can be quite balmy. During the summer, reaching about 70 Fahrenheit or 20 Celsius. What would this be in Kelvin? Okay. So the value given here is in degrees Celsius. That's the temperature. It's in degrees Celsius. And then we want to convert this degree Celsius into Kelvin. So we can use this. To convert to Kelvin, we add degrees Celsius to 273. So therefore we'll have 20 plus 273. And this will give us 293 Kelvin. Okay. So the temperature of 20 degrees Celsius will be equivalent to 293 Kelvin. Standard temperature is considered to be 273 Kelvin. What is this temperature in Celsius? Okay. So this time around, we want to convert from Kelvin to degrees Celsius. So we'll use this equation here. or we'll use this formula, that is K minus 273. And K is already 273, so therefore this will be 273 minus 273, which will be equal to 0 degrees Celsius. Okay. So 273 Kelvin is equal to 0 degrees Celsius. Water freezes at about 0 degrees Celsius. What would absolute temperature does water freeze? Okay. So here we need to convert degrees Celsius into Kelvin, and our temperature in degrees Celsius is 0. And we need to add 273 in order to convert it into Kelvin. So 0 plus 273 will give us 273 Kelvin. So that means water freezes at 273 Kelvin. Room temperature is about 20 degrees Celsius. What temperature is that in Kelvin? That is something we've calculated before. It's going to be 293 Kelvin. Kinetic molecular theory. Kinetic energy before collision is equal to kinetic energy after collision. Collisions between gas molecules are perfectly elastic, meaning that there is not net loss in kinetic energy over the course of the collision, meaning the energy before collision is equal to the energy after collision, meaning the energy of the gas molecules before collision is equal to the energy of the gas molecules after collision. And we call this type of collision as perfectly elastic. The fourth premises is that because of their extremely low density, we assume that the gas molecules occupy a negligible amount of space in a container. Therefore, the volume of the container is essentially the volume occupied by the gas. So this is a summary of the four premises that we've talked about, or we can call them the postulates of what? The kinetic theory of gases. The first one is gas molecules are in constant motion and therefore possesses kinetic energy. And then the second postulate is average kinetic energy of gases is proportional to the temperature. The third postulate is that collisions between gas molecules are elastic. Okay. And then the fourth postulate is gases occupy a negligible amount of space in the container. Now let's look at the properties of gases. Properties of gases. Characteristics of gases. The gaseous state is characterized by extremely weak interactions between the atoms, ions, and molecules. So that means essentially no bonds. Okay. Since there are very few attractions between gas molecules are free to move and will expand to fill their containers. For example, if you have a container that has some gas molecules and then a piston placed on top of this, okay, the gas molecules can expand. If they expand, the piston is going to push up. So when the gas molecules expands, the volume is going to increase, as we can see between the first and then the second, that is A and B. At A, this was the initial volume of gases, but B is as a result of what? The expansion of gas molecules in A. Characteristics of gases. Since there are very few attractions between gas molecules, a small number of molecules can occupy a large volume, resulting in very low densities. Okay? So these are some physical states of water, that is ice, liquid, and then vapor. Okay? And then the density of ice is 0.91 grams per milliliter, and then the density of liquid water is 0.98 grams per milliliter, and then the density of gas in the form of vapor is 0.00052 grams per milliliter. So this shows that gases have very low densities compared to liquid and ice. Generally, solids have higher density than liquids and then gases. Since gases have much lower densities, meaning very few molecules in a very large space, they can be compressed into a much smaller volume. Okay? Because gases will occupy a huge or a large volume, we can easily compress them. And in compressing gases, what do? We try to reduce the intermolecular distances between the gas particles. So you reduce the distance between the gas molecules. So let's answer this question, which of the following would not describe the gaseous state of matter? That is high compressibility, A, B, strong intermolecular attractions, C, low density, D, will expand to field container, and E, particles are in motion. Which of the following would not describe the gaseous state of matter? The correct answer here is B, strong intermolecular attractions. Which of the following would be true regarding the gaseous state? A, gases are slightly less denser than the liquid state. B, gases have attractive forces similar to that of other states. C, the volume of a gas can change far more than that of a solid or liquid. D, gas molecules weigh less than molecules in the liquid or solid state. And E, none of these are true. Okay, with regards to this question, letter B is the correct answer. That is, gases have attractive forces similar to that of other states. That's wrong. Okay. Gases, the attractive forces cannot be compared to the attractive forces in other states. Next, we look at measuring pressure. In order to understand gases, we measure 4 variables. Okay? And these are the variables that we'll interact with looking at the gas laws. One of the variables is pressure. Another variable is temperature, volume, and number of moles. So we'll discuss first in describing how we measure pressure and temperature before discussing the relationship between these 4 variables. A key characteristic of gases is their pressure. First, we look at pressure. A key characteristic of gases is their pressure, how much force they exert on their container. So pressure is the amount of force applied per unit area. The magnitude of pressure is given by So this means the greater the force, the larger the pressure. Okay? And the greater the surface area, or the greater the area, the smaller the pressure. So the SI units of pressure can be found from this formula. That is, pressure equals to force over area, where force is measured in newtons and the area is measured in meters square. So therefore, the SI unit for pressure would be newtons per meter square, which is also called Pascal. And we write capital P small a, okay, as the unit for Pascal. So these are the SI units of pressure, newtons per meter square, and then Pascal. So let's take a look at this example here. A chemistry textbook is placed on a table. The same force can result in very different pressures. If a book is placed on a table in a flat position, its weight exerts a pressure over a greater area than it is placed on its edge. So these are the 2 diagrams. One of them, the textbook is placed on its surface, and then it covers a large area. And then the second diagram shows that the book is placed on its edge, and then it covers a smaller area. Okay. Coming back to this formula here, if area should be greater with a small force, then the pressure will be less. Okay. But if the force is greater than the area, then we'll have a large pressure. So in the first instance, where we have what the book placed on its surface, we have what a larger area. So therefore, it will exert a low pressure or less pressure. But in the second diagram, we have the book placed on its edge, and therefore it will have what? A smaller area, and then the force will be greater, therefore the pressure will also be large. Atmospheric pressure is the weight of air per unit area. So a 1.0 meter square column of air extending to outer spaces has a weight of 101,000 newtons or 101 kilonewtons. So the pressure exerted by any fluid, including gases, is always perpendicular to any surface. As there is no direction associated with pressure, it is a scalar quantity. That is, it has only magnitude but no direction. Okay. So the barometer is a device for measuring atmospheric pressure at a particular time and place. As weather systems move through, the mercury rises and then falls as the local atmospheric pressure changes. However, standard atmospheric pressure of 1 atmosphere or 101 kilopascal supports a column of mercury which is 760 millimeter tall. So that means 1 atmosphere will be equal to 760 millimeter mercury. This is another unit of what? Pressure. Okay. And this is equivalent to 760 ton. Okay. Standard pressure. What do we call standard pressure? Normal atmospheric pressure at sea level is referred to as standard pressure, and it is equal to all of the values below. That is 1 atmosphere, 760 millimeter mercury, 101 kilopascal, and then 760 torr or 1.01 bar. Let's look at this question. What is the pressure and temperature in Kelvin at standard conditions? That is STP. Okay. Standard temperature is 273 Kelvin. And then standard pressure is 1 atmosphere. So therefore, letter A is correct. After looking at the 4 variables, which are number of moles, volume, pressure, and temperature, we're going to look at gas laws. Under this, we're going to look at the behavior of gases. How do gases behave under certain conditions? That is, under temperature, or changes in what? Pressure, or changes in what? The amount of substance, or changes in the temperature. We'll now look at the relationships between the 4 variables of a gas: pressure, volume, temperature, and number of moles. Okay. In order to study the effect of one variable on another, we must keep the other variables constant. So 4 laws were eventually combined to create the ideal gas law. These 4 laws show the relationship between the 4 variables under different conditions. And then they are Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. So first we look at the relationship between pressure and volume. What is the relationship between pressure and volume when the other 2 variables are kept at constant? Okay, which will be temperature and then the number of moles or the amount of substance. If the volume of a container is increased at a constant temperature, a fixed quantity of gas molecules will collide less, often with the container resulting in a proportional drop in pressure. This is an inverse relationship, meaning P is inversely related to what? Volume. Okay. That is, if P increases, volume will decrease. If P decreases, volume will increase. Okay. Diagram here, V is equals to 2 liters, and then the pressure is 32 millimeter mercury. You have more collisions. But V changes to 4 liters, and then P also changes to 16 millimeter mercury. So V is increasing from the first to the second one, but look at what happens to P. P is decreasing. So whatever factor that V increases by, P will also decrease by the same factor. So if you look at the difference between 2 and 4, V has increased by a factor of 2, and then P has decreased by a factor of 2. And then we'll expect what? Fewer collisions where V is 4. So this relationship is studied by a scientist called BOYLE'S. And we call it the Boyle's law. Okay. So the Boyle's law looks at the relationship between pressure and volume. Okay. And he used a graph to represent the relationship. Yeah? That is P and V. So the graph shows that as P increases, V is reducing. But as V increases, P is reducing. P is increasing from the margin, that is from 0 going up. And then V is increasing from 0 going towards the right. The graph is a summary of the relationship between P and V. Boyle's law states that for a given mass of a gas at constant temperature, the volume of the gas varies inversely with pressure. So in an inverse relationship, the product of the two variable quantities is constant. So the product of pressure and volume at any two sets of pressure and volume conditions is always constant at a given temperature. So the mathematical expressions of Boyle's law is as follows. The relationship is P is inversely proportional to V. So if you change the proportionality constant with an equal sign, we'll have P equals to K over V. Okay. Making K the subject of the formula, we'll have P, V is equals to K. Okay. That is, the product of P and V is always a constant. Okay. And if the conditions of these two variables should change, then there will be changes in pressure and volume as well. And as a result, we'll have P1, V1 equals to P2, V2. Okay. And we'll use this formula in our calculations. So let's try to answer this question. If the volume of a gas is decreased, the pressure will also decrease. True or false? So according to the law, P is inversely proportional to V, meaning when one variable increases, the other should decrease. But here it is saying both variables are decreasing. So therefore, the answer is false. Let's look at few sample questions. The first question reads, a gas with a volume of 4 cubic decimeter at a pressure of 205 kilopascal is allowed to expand to a volume of 12.0 cubic decimeter. So we have two different volumes here. We have our initial volume and then the final volume. The initial volume is given as 4.00 cubic decimeter. And then the final volume is given as 12.0 cubic decimeter. Okay. And then the initial pressure is given as 205 kilopascal. And the question is, calculate the final pressure at constant temperature. So the relationship between pressure and volume is inverse. So that is P1 V1 is equals to P2 V2. Since we need to calculate P2, we can make that as the subject of the formula. So therefore, P2 will be, okay. So we substitute, V1 is given as 4, P1 is given as 205, and then V2 is given as 12. Our answer is 68.3. Okay. Since the unit of pressure is in kilopascals, our answer is going to be in kilopascals. Okay. So looking at the answer, it makes sense. Why? Because volume is increasing. So obviously pressure should decrease. Okay. If volume increases, pressure should decrease. The next question reads, nitrous oxide is used as an anesthetic. The pressure on 2.5 cubic decimeter, that's our initial volume, 2.5 cubic decimeter, changes from 105 kilopascal, that is P1, 105 kilopascal, to 40.5 kilopascal. P2 is given as 40.5 kilopascal. If the temperature does not change, what will the new volume be? We write our formula, P1 V1 equals to P2 V2. And in this question, we know V1, we know P1, and we know P2, but we don't know V2. So V2 will be P1 V1 all over P2. If you substitute, we'll have P1 is 105 times V1 is 2.5 divided by our answer is V2 is 6.48 cubic decimeter. So let's look at this answer. Pressure has reduced from 105 to 40.5. So obviously, volume should increase. Okay? And here, volume is 2.5, and it has increased to 6.48. So the answer makes sense. And the final question is, if a gas is compressed from 4 cubic decimeter to 1 cubic decimeter, and the temperature remains constant, what happens to the pressure? Okay. Here you have to take into consideration of what? The relationship between pressure and volume. The relationship is inverse, meaning when pressure increases, the volume should decrease. So here, the volume is reducing from 4 cubic decimeter to 1 cubic decimeter. So it has reduced by a factor of 4. Therefore, the pressure is going to quadruple. It has to increase by a factor of 4. Okay. That brings us to the end of the lesson. Until we meet next, bye for now.